Okay, great. So yeah, welcome everybody. We're very pleased to have Bruce Berndt with us today. And I want to say a few words about Bruce. So Bruce, as you can see from the title, he's speaking about the work of Ramanujan, which I'm also very excited about and has inspired a lot of my work. And there's a lot of amazing things to say about Ramanujan that I think Bruce will be telling us about. And Bruce is a distinguished expert on the work of Ramanujan. He has a famous series of works, also together with George Andrews on some of them. He's written about the lost notebooks of Ramanujan that he'll be talking about today. And Bruce has painstakingly worked through these notebooks and provided proofs of now all of the work, all of the entries in all of the lost notebooks, and all of there's a whole series of books, and all of them have now finally been published and are in print. And it's an amazing achievement of Bruce. And he has had a distinguished career. He's received the Lester R. Ford Award for exposition, I believe, twice. He's got the Steele Prize. He's a fellow of the AMS and was the Michio Suzuki Distinguished Research Professor of Mathematics at the University of Illinois. And he's really, been a long-term leader in the community in analytic number theory. He has 36 graduated PhD students, 10 postdocs, 237 papers, 14 books. And I think he'll be telling us some cool stuff that I think will be interesting for a general audience today. And as you can see on the screen, his title is Ramanujan, A Century of Inspiration.
Oh, thank you, Larry. Before I start, I would just like to express my concern for all those who have lost loved ones, who have suffered serious illness, and who have encountered economic hardship due to COVID-19. It's been a hard year for many people in this respect. So let me just outline the lecture. So this is a very general lecture, so I'll say quite a bit about the life of Ramanujan, the history of Ramanujan's notebooks, and the history of the lost notebook of Ramanujan. So then I hope you'll permit me to say a few words about the 46 years that I've worked on Ramanujan's notebooks and lost notebook. And then I'll give examples from both the notebooks, the earlier notebooks of Ramanujan, and the lost notebook. So I'd like to begin with the 4 photographs that we have of Ramanujan. Now, this is the most famous of the 4 photographs. It's his passport photo taken in 1919 before he returned to India. The passport photo and passport were in the possession of his widow, Janaki, and they were retrieved by S. Chandrasekhar, the famous Nobel Prize winning physicist, when he visited India in 1936. Hardy had asked if he could find a photograph of Ramanujan on his visit to India, and he visited Mrs. Ramanujan, and she loaned him his passport on which this photograph was taken. So he looks like he's in a suit, but in fact this is a bathrobe, and these are his pajamas. He was too ill to go to the photographer to have his picture taken for the passport. So in this picture, he's at the center, and you will notice his countenance is much fuller than in the passport photo. This was taken in 1916 when Ramanujan got a degree by research at Cambridge University. By the time the passport photo was taken, he had lost considerable weight. And this picture was taken, we don't know exactly when, but sometime at Cambridge. So let me tell you about, just briefly about the people in the photograph. This is K. Ananda Rao, who was a student of Hardy, and he was a quite well-known analyst in India for some years.
I don't think we are sharing the picture with us.
Did the picture go away?
I can see it.
I can see it.
And also, can you hear me okay?
Yes.
Yeah, I can see and hear you.
Okay.
Akram, can you?
Okay, so this person here, I always have to check my notes here. Settler Sundara Surya Narayana Shastri. He got his degree at Oxford and is a philosopher, and for many years was one of India's leading philosophers at the University of Madras. And this person is also a mathematician. His name is Taneti Surya Narayana. He came from a very poor family in India and returned, and he was mostly known as a great teacher. And this person here is Adi Narayana Chetty. He happened to be born in the same town as Ramanujan, Kumbakonam, and was one of Gandhi's principal followers in the fight for independence. So this was a picture taken of Ramanujan at the same setting, I believe. So let me get to Ramanujan's life. He was born in the southern Indian town of Baroda in the home of his maternal grandmother. And then after a couple months, his mother and him returned to Kumbakonam. And this is the home in which they lived for many years. I visited this in 1986 and took this picture. Now the home has been turned into a museum, so it doesn't look anything like the original home. The only indication that this was Ramanujan's home was that the family living in it had taken a picture of Ramanujan that they found in a newspaper and typed it above the entrance. So this entrance is just inside the bamboo curtain that you saw in the previous photograph. So I was accompanied by Balasubramanian, who was head of math science in Madras for some years. Maybe he still is head of math science there. So there were several people living in the home. This is the father, this is 7 of his children. Also a set of grandparents lived in this very small home of essentially 3 different rooms. So when Ramanujan was a student in Kumbakonam, he worked on a slate, as all students did at that time. Paper was very expensive. And this is actually Ramanujan's slate. It's actually in the family of S. Narayana Iyer. This is his grandson who has passed away now. And I'll tell you in just a few minutes how this slate of Ramanujan happens to be in the family of S. Narayana Iyer. This is my favorite picture of myself holding the slate. My wife disagrees with this. She feels our wedding picture should be my favorite picture. Well, it's about half and half, let's just say. Yeah. Well, Ramanujan entered the government college of Kumbakonam at the age of 16, but he wouldn't study anything except mathematics. And after 1 year there, he didn't pass his exams other than mathematics, and he had to drop out. He tried again to get a college education in 1906 at Peshayappa College in Madras, but the same thing happened. He wouldn't study any other subjects. He married in 1909. His wife, Janaki, was just 9 years old at the time of the marriage. So he tried to seek a job. So he went to Madras in 1910. And for 2 years, he was supported by a mathematician who was actually a collector in the Madras Civil Service. His name was V. Narayana Iyer. And Ramanujan felt that he shouldn't be, not have a job without doing work. So it bothered him a bit. And so he applied to be a clerk at the Madras Port Trust Office, where S. Narayana Iyer was the chief accountant there. So S. Narayana Iyer was actually one of the best mathematicians in India at that time. And he and Ramanujan often worked together on mathematics after their day at the Madras Port Trust ended. So Narayana Iyer and the chair of the Port Trust Office, Sir Francis Spring, encouraged Ramanujan to write English mathematicians about his work. So he first wrote M.J.M. Hill at the University of London, who responded, but clearly did not understand the mathematics that Ramanujan communicated in his letter. And then he wrote two Cambridge mathematicians, E.W. Hobson and H.F. Baker, and neither of them replied. And then finally in January of 1913, he wrote G.H. Hardy. So this letter to Hardy contained over 60 results without proofs. And Hardy first dismissed the letter, but that night he and Littlewood went over the letter and saw that there were many results that they could not prove, in which they conjectured were true. And Hardy then immediately wrote Ramanujan, urging him to come to England so that his talents could be more fully developed. So Ramanujan's family and was against him going to England. Ramanujan wrote a second letter to Hardy with another 60 results, and Hardy again wrote back asking him to come to England. So in March of 1914, after getting the approval of especially his mother, Ramanujan did go to England with Hardy, and then became very famous for the work that he was doing in England. Let me just give you a few results from the first letter that Hardy received from Ramanujan. So this one, 1, 2, 4, 5, 8, 9, 10, 13, 16, 17 are the numbers which are either themselves squares or which can be represented as a sum of two squares. Then Ramanujan claimed that the number of such numbers greater than A and less than B is, as you see on the screen. He gives the numerical value of K, says that theta of X is very small compared with the integral, and that K and theta of X have been exactly found, though complicated. Note there's a slight misprint here. He should have theta of B. The constant actually is found in his notebooks, and he probably was a bit optimistic about the size of theta of X. So this is one of the results that Hardy was greatly impressed with, because here Ramanujan arrived at a result which European mathematicians might arrive at. And Ramanujan had no connection with mathematics outside of India. And so he didn't have any connections with thinking about the prime number theorem, which he also discovered on his own. And so Hardy, indeed, as others thought, it was very remarkable that he could find such a problem or himself and attack it. There are a number of results on integrals, which Ramanujan always loved in the first letter. So here we have the quotient of infinite products here, and it's evaluated in terms of gamma functions. This is another integral evaluation from the first letter. I always thought it was very interesting because we have the function and it's reciprocal here. So it's some type of inversion formula involving the cosine and the sine in the integral. And he evaluated phi at many different values. You note a couple of them have pi in, but the others don't. So there doesn't seem to be any general pattern, but it might be worth investigating. No one really has. If one can find some pattern or formula in the values of phi. So Ramanujan, in the last 2 years of his 5-year stay in Cambridge, became very ill, but you can see from this letter that he wrote to a friend in Madras that already at the end of 1 year in England, he was not feeling well. And then, as I indicated, after 3 years, he was very seriously ill, and for the next 2 years, he was in and out of several nursing homes and sanitaria. Yeah. So this is a quote from Hardy to Mittag Leffler in August of 2017. In 1918, he was elected as a Fellow of the Royal Society. So these are those at the ceremony who had voted for him. These three in italics voted for him but weren't actually at the ceremony. So you will note the names of Hobson and Baker, who never responded to Ramanujan's earlier letters. So a year later, Hardy found that he had improved in his health. So he says, I think we may now hope that he has turned the corner and is on the road to a real recovery. His temperature has ceased to be irregular, and he has gained nearly a stone in weight. The consensus of medical opinion is that he has been suffering from some obscure and only partially diagnosed source of blood poisoning, which is now dried up. Well, this diagnosis, unfortunately, was, well, maybe fortunately or unfortunately not correct. There were other diagnoses that were made, tuberculosis, not getting proper food because he was there during World War I. He couldn't get food from India. And some said some kind of virus or bacteria that they didn't know about. But many years later, an English mathematician by the name of D.A.B. Young examined all of the descriptions of Ramanujan's illness that he could find and concluded that Ramanujan died of hepatic amoebiasis, which is an amoebic infection of the liver, if dysentery is not treated properly. And it appears that Ramanujan had 2 bouts of dysentery before he went to England. So he said, if dysentery is not treated properly, then the amoeba will live in your large intestinal area. It may not bother you for some time, but if your lifestyle is changed, as Ramanujan's obviously was, going to a colder climate, then the amoeba could act up and would kill you. So there was a treatment for that at the time. It's just unfortunate that dysentery was not recognized as the cause of his illness. Well, Ramanujan returned to India in 1919, in March of 1919, and wrote Hardy only 1 letter before he died on April 26, 1920, at the age of 32. This letter is one of the most famous letters in the history of mathematics, and I'll say a few more words about it later. So it was suggested that Ramanujan's notebooks that he accumulated his results in over a period of several years and his published papers be collected together for publication. But at the time of publication in 1927, only his published papers were given. So let me say a few words about his notebooks. Ramanujan started to collect his papers or his theorems and notebooks about the time we think he entered the Government College of Kumbakonam in 1903. And he evidently recorded his results up until 1914 when he left for England. So the notebooks cover a period of about 10 or 11 years. So say a few more words, give more details about the notebooks later. We think that he might have left 1 notebook in India, but we're not sure. Before he went to India or to England, Ramanujan exchanged slates with S. Narayana Iyer. And this is why the family of S. Narayana Iyer has the slate now. So it was a sign of respect for each other that they exchanged slates before he left them. So we think that these 10 years before he left for England are the years in which Ramanujan recorded results in notebooks. So I'll say more about them now, but I'll say just a few more words now about the notebooks. In regard to the collected papers, if you're very careful when you look at this, you'll find there's something unusual here. I'll give you a few seconds to think about it. Is there something unusual with this title page? Well, B.M. Wilson's name is in larger print than Hardy and PVS Seshu Iyer. So evidently, Hardy felt that Wilson was the one, well, indeed he was, who put all this together. And so his name should be in slightly larger print. P.V. Seshu Iyer was Ramanujan's teacher in his 1 year at the Government College of Kumbhakonam. So after the publication of his collected papers, B.M. Wilson and G.N. Watson began to edit the notebooks. So Wilson worked on this project for 5 years, but then unfortunately died after getting an infection in the hospital. And then Watson worked on the project for about 10 years or so before his interest declined. So I think this is all I'll say about the main things in Ramanujan's life. So now let me just give you more of a history of Ramanujan's notebooks now. Okay, so I'll just repeat that they're from the period from about 1903 or 1904 to 1914 when Ramanujan left for Cambridge. So on January 7th, 1915, Ramanujan wrote to another friend in India, "I am doing my work very slowly. My notebook is sleeping in a corner for these 4 or 5 months. I am publishing only my present researches as I have not proved the results in my notebook rigorously." So this seems to indicate that he was not recording any more results in his notebook after he got to England. Okay, now let me jump ahead to 3 years after Ramanujan died. This is a letter from the Francis Dewsbury, Registrar at the University of Madras, to Hardy. "I have now seen your letter dated 19th of November 1921 to Mr. Kayananda Rao," so remember he was one of Hardy's students, "in which you state that you have one of the late Mr. Ramanujan's notebooks with you. I shall be glad if you will return the original notebook when you have extracted from it the selected matter for printing in the memorial volume." So that notebook, which Ramanujan mentioned in his letter, is the notebook that actually Ramanujan did leave with Hardy. Now it turns out that Ramanujan had a second notebook, which was in Dewsbury's possession. Dewsbury thought he had the first notebook, but in fact he had the second notebook. The first notebook is what Ramanujan left for Hardy. There are actually 3 notebooks. The third one is very short. So they are now bound and kept at the University of Madras. So the first volume contains the first notebook. This is the second notebook, which is a revised, enlarged edition of the first. However, in my work on the notebooks, I found that there are about 200 results in the first notebook that are not in the second notebook. So the second notebook is the primary notebook. The third notebook is actually very short. It only has 33 pages. So I took that picture, and I took another picture. This was back in, I think, 1986. You will note that there is a reflection on the page. And the reason there is a reflection is that I must tell the younger members of the audience that we didn't have cameras and iPhones in those days. If we were indoors, we had to use a flash bulb in taking a picture. So my flash bulb reflected off of this page. Then you might ask, why should there be a reflection? Well, it turns out that insects were destroying the notebooks. And so the librarians laminated the pages of the notebooks. And so this is why you see a reflection here. So the Tata Institute of Fundamental Research in Bombay didn't publish the notebooks until 1957. So here is my copy of the notebooks. The first notebook contains the first volume contains the first notebook, and the second contains the second and third. So I took this picture in my home about a year ago. And then in 2012, on the 125th anniversary of Ramanujan's birth, a second edition of the notebooks was printed. And at that time, they said that the lamination was not good for the notebooks. The lamination was cracking. So they removed actually the lamination. And I think now the notebooks are kept in a more controlled environment. So let me just indicate in a few minutes how I became interested in the notebooks. I was a graduate student at the University of Wisconsin, and I never had any course in number theory until the third year, spring of my third year, when I took a course in modular forms from Rod Smart. And then in the following fall semester, I took a course from Marvin Knopp on modular forms with applications to number theory. And here I learned about Ramanujan for the first time. In particular, he established the Hardy-Littlewood circle method and told us about the congruences for the partition function. I never had a course from Richard Askey, but he remained very influential in my life during my entire career. My thesis contained Bessel functions, and so my thesis was actually of interest to Dick Askey, and I regret that he died about 1 year ago. I miss his guidance very much. So I went to the University of Glasgow for 1 year, where my mentor was Robert Rankin. Rankin was actually the last PhD student of G.H. Hardy. And I'll come back later to Rankin. So I took a job as an assistant professor at the University of Illinois, where Paul Bateman was the head of the department. To tell you the truth, I hadn't really planned on going to the University of Illinois. I had done my undergraduate work at a small liberal arts college and intended to go back to a small liberal arts college for my career. But I thought I might go to Illinois for maybe a couple years and then go on to a liberal arts college. But I still haven't gotten to a liberal arts college. So in my second or third year at Illinois, Paul Bateman asked me to referee 2 papers that he received to referee. And you can see these papers of Grosswald prove formulas in Ramanujan's notebooks. Here's a photograph of Grosswald. So I went to the Institute for Advanced Study for my first sabbatical. And in one day in February of 1974, I saw that the work that I was doing on Eisenstein series and transformation formulas, I could use this work to prove all these formulas that Grosswald had proved from Ramanujan's notebooks. So this was a very exciting moment for me. So I went to the Princeton University Library to borrow the notebooks, found a few more theorems I could prove from the notebooks, but a few thousand others that I could not prove. So when I went home after sabbatical, I didn't really do anything as far as the notebooks were concerned, I did try to use my methods to get as many results as I could. But then in May of 1977, I said to myself at the close of the spring semester, let's try to prove everything in chapter 14 of the second notebook. This is the chapter in which the formulas that Grosswald had proven are found. So let me just indicate one of these formulas. This is a formula involving the Riemann zeta function. So as most of you know, the Riemann zeta function at positive even integers can be represented as a rational multiple of pi to the 2n, if 2n is the power of the integers in the denominator. But we have no knowledge of the zeta function at odd integers, positive integers, except that we know from a priori that zeta of 3 is irrational. So I've always liked this formula very much. The BK here are Bernoulli numbers, and they're rational numbers. So if you specialize it by letting alpha and beta both be pi, replace n by 2n plus 1, you get this formula for zeta of 4n plus 3, which is actually due to Lerch in 1901. So I like this formula because you see that zeta of 4n plus 3 is almost a rational multiple of pi to the 4n plus 3. So there's an error term, a very rapidly convergent series. So I say in a very non-mathematical way that zeta of 4n plus 3 is almost a rational multiple of pi to the 4n plus 3. So I worked on chapter, so in fact, here are here's the page in the notebooks where those two formulas are found. Well, let me just say a few more words about my work on the notebooks. After working on chapter 14 for over a year, George Andrews visited Illinois in the fall of 1978. And he told me that the efforts that Watson and Wilson had made to edit the notebooks from about 1927 to the late 1930s were fortunately preserved in the library at Trinity College. So I wrote Trinity College, Cambridge for a copy of their notes, and they kindly sent them to me. And so then I went back to the beginning and gradually worked my way through the notebooks, and their notes were very helpful on certain chapters. So I worked on this for a little over 20 years, and I was greatly helped by my graduate students. In particular, Ron Evans and Heng-Hua Chan helped quite a bit, but there are many other students that helped as well. So Evans had his career at the University of California at San Diego, and Heng-Hua Chan is a professor at the National University of Singapore. So as I said, I worked on this for about 20 years before I then started to work with George Andrews on the Lost Notebook. So let me just say a few words about some of the topics in the notebooks. So there's quite a few results on Q series. So let me define AQ sub n as this product of 1 minus AQ to the k running from 0 to n minus 1. And if the absolute value or modulus of Q is less than 1, we can take the limit as n tends to infinity. So not all Q series have these products in them, but except for theta functions, which I'll define next, which are part of the theory of Q series. And a few other series, most of them have these Q products in them. So this is Ramanujan's definition of a general theta function. It's not the definition that Jacobi gave for a general theta function, but it expresses the symmetry here. Ramanujan always loved symmetry. If he could express a theorem or formula in a symmetric way, this is the way he always did it. So for most people working in theta functions, this is not the best definition, but for Ramanujan, this was the best definition. So here we have the Jacobi triple product identity representation of the theta function, f of AB. And these are the three most interesting cases. Phi of q in Ramanujan's notation is f of q. Psi of q is f of q cubed, and I've taken the negative index terms and wrapped them up with the positive index terms. And then f of minus q minus q squared. This is just q sub infinity by the Jacobi triple product representation. And this is essentially the Dedekind function. So let me just say a few words about notation. Ramanujan actually never used this notation. He would always just write out the first few terms of a Q product until it was clear what the general terms were. He didn't use any of the standard notation for theta functions, and he derived many properties of elliptic functions, but he didn't use any of the standard notation there as well. I'm going to say a few words about the complete elliptic integral of the first kind. So this is its definition, k of k. If you expand the integrand in a binomial series, you get this. And now here I'm using the rising factorial or shifted factorial notation. Unfortunately, it's essentially the same as the Q product notation. And you can identify this as a hypergeometric function. So k is what's called the modulus, and k prime, the square root of 1 minus k squared, is the complementary modulus. So here is a definition of a modular equation. This seems unmotivated, but I'll skip all the motivation because I don't have time to do so. So these are elliptic integrals associated with the moduli k, k prime, l, and l prime. And we assume for a positive integer n that we have this relation amongst these four integrals. Then a modular equation of degree n is a relation between these moduli k and l, which is induced or implied by this equality. So Ramanujan doesn't use the standard notation. He lets alpha be k squared and beta to be l squared. And actually, Ramanujan very seldom used the complete elliptic integral notation. He wrote this equation in terms of hypergeometric functions. So in his notebooks, Ramanujan has over 100 modular equations. So I've just given 3. You'll be pleased that I won't give you all 100 and some. And in fact, for certain degrees, he has many modular equations. For degree 3, he has over a dozen. So note that these are all different. They have a nice symmetry. And in fact, if you have a modular equation of any prime degree, it does not repeat itself. So in other words, this modular equation of degree 3 only happens for degree 3. It doesn't happen for any other prime degrees. Okay, so let me just summarize what one can find in the notebooks. There are lots of identities involving infinite series. A lot of work on theta functions and elliptic functions. Fair amount of work on hypergeometric functions. And I've mentioned Q series and basic hypergeometric series, which always have those Q products and integrands. And then quite a bit of work on number theory. So now let me head to Ramanujan's lost notebook. So I'm quoting here from the Bhagavad Gita, so some sacred writings. Through long lapse of time, this knowledge was lost, but now as you are devoted to truth, I will reveal the supreme secret. So this was written, as I recall, in the 6th century. And I think the you here is George Andrews. So he is devoted to truth, and the supreme secret is the lost notebook. So the lost notebook was found in the spring of 1976 by George in the library at Trinity College, Cambridge. When he visited there, he was advised by Dr. Lucy Slater that he might find it interesting to go through the papers of the late G.N. Watson. So here is George with his daughters, Amy and Katie, and Lucy Slater. So let me just give you a few pages from the Lost Notebook. It was published in 1988. So it's just full of formulas in a very closely written style. And again, as in the earlier notebooks, there are no proofs. Here's a page which is very difficult to read. There, I think, as I recall, 153 pages in this notebook. It's really not a notebook, but just a sheaf of papers. And I think this page was very thin, maybe a piece of parchment paper. And so the photographer really photographed two sides here for this page or for pages. So the big question is, how did this manuscript of over 100 pages reach the library at Trinity College? So I think we can trace its path. So let me return again to the registrar at the University of Madras, Francis Dewsbury. He wrote to Hardy, I have the honor to advise dispatch today to your address per registered and insured partial post of the 4 manuscript notebooks referred to in my letter 6796. So we really don't know what the 4 means here. We don't think it was really 4 notebooks. As I indicated before, it appears Ramanujan had just 3 notebooks that he left. So we're assuming actually he put these papers into 4 stacks maybe. We are not sure. But almost certainly this parcel post included Ramanujan's lost notebook. And there were many other papers published with the Ramanujan's lost notebook in 1988. And all of these papers, or at least many of them, were undoubtedly in this packet that Ramanujan, or that Francis Dewsbury sent to Hardy. He also said in the letter, please return them in due course. Hardy evidently never returned any of them. So I mentioned Watson had done a lot of work on Ramanujan's notebooks. He had also done work on Ramanujan's lost notebook. So we think that Hardy passed on to Watson the lost notebook in the late 1930s. We're not sure exactly when he passed the lost notebook on to Watson. He wrote a paper on an account of the Mach theta functions, which were in Ramanujan's, the chief topic in Ramanujan's last letter to Hardy. This was his presidential address, or really expanded version of his presidential address in 1936. So in this presidential address, he said, well, here are some Mach theta functions that Ramanujan didn't discover. Well, if he had looked carefully, or if he had the lost notebook, he would have seen that Ramanujan had actually discovered these theta functions, 3rd order Mach theta functions. So he took the title from The Adventure of the Final Problem, one of the Sherlock Holmes stories written by Sir Arthur Conan Doyle. And it was his 24th and final short story about Sherlock Holmes. And Dr. Watson was Sherlock Holmes' sidekick during all of these stories. So there are then at least 2 reasons why Watson chose this title for his retiring presidential address and this paper in the Journal of the London Mathematical Society. So possibly then the lost notebook was passed on to Watson then after he gave this address. Well, Watson was professor of mathematics at the University of Birmingham for his entire career. And he died in 1965. And then shortly thereafter, Robert Rankin visited his widow. Rankin had actually succeeded Watson as Mason Professor of Mathematics at the University of Birmingham upon Watson's retirement, but then had gone on to the University of Glasgow to become Professor of Mathematics there. So he and Mrs. Watson discussed what they should do with her late husband's papers. So they decided that since he had been a fellow at Trinity College and had always been very fond of Trinity College, Cambridge, that what Rankin should do is to sort through all these papers and those worth preserving be sent to Trinity College. So over a period of over 3 years, Rankin took train trips to visit Mrs. Watson and sort through these papers. So in fact, in this 3-year period is when during this 3-year period was the year I spent at the University of Glasgow. And I regret that I don't remember a conversation that I had with Rankin in his office one day about Ramanujan. He did tell me about the notebooks of Ramanujan for the first time, but unfortunately I don't remember if he told me about the papers that he found of Ramanujan with Watson's papers. So he sent Ramanujan's papers in December of 1968 to Trinity College Library, but he didn't tell anyone else about these papers for Ramanujan. So there they sat for about 7.5 years until George Andrews then rediscovered them in March of 1976. So we think that's the story of how Ramanujan's lost notebook reached Trinity College. So let me say a few words about topics in Ramanujan's notebooks, lost notebook, and I'm a bit running out of time here. So again, there are a lot of results on Q series in the lost notebook. So if you take a typical Q product, replace Q by Q to the A, divide through by 1 minus Q to the N, apply L'Hopital's rule, then you get the rising factorial. So a lot of results in the theory of hypergeometric functions have corresponding results in terms of Q series. So here is the Q binomial theorem, for example. Let me just go. So there are a number of results on false theta functions and partial theta functions. A false theta function is a theta function, but the signs maybe have been changed for an infinite number of terms. So this is the function psi of x about which I told you earlier, except now we have minus 1 to the n inserted. Now this is a partial theta function. A partial theta function is one where you only take usually the terms from 0 or 1 to infinity and leave off the other terms. So this is an identity from Ramanujan's lost notebook. So in Ramanujan's last letter, he introduced Mach theta functions. So only go through this briefly here. So in this letter of January 12th, he said that he's examined asymptotic behavior of Q series as t tends to 0, where Q is e to the minus t. Here I've given the little o of 1 notation. We say that a function is little o of 1 as x tends to a if the limit of f of x is 0 as x tends to a. So he says the series above is a reciprocal of a theta function, namely it's the reciprocal of f of minus q. And then he asks if the converse is true. That is, suppose we have a Q series that exhibits an asymptotic behavior of the kind described here as we approach an exponential singularity of the function. Must the function actually be a theta function plus some easily described trivial function? So Ramanujan says not necessarily so. When it is not so, I call the function the Mach theta functions. Okay, so I'll leave it to Larry to discuss Mach theta functions in his class and in seminars at Vanderbilt. So let me just skip over the results on Mach theta functions. Let me mention one more result on Q series, found actually in Ramanujan's earlier notebooks as well as the lost notebook. And Ramanujan used his summation formula many times in his work on Q series. So he extends the definition of AQN to negative integers by this formula. So this identity here is over the negative and the positive integers, as you can see. So it's an analog of the Jacobi triple product identity. A lot of results on Eisenstein series in the lost notebook. So in the notation of modular forms, E4 of tau is Q and E6 of tau is R. There were many manuscripts of Ramanujan published with the lost notebook. And for many of them, we have only their copies in the handwriting of Watson. We do not have the original copies. And the most famous of these are these 40 identities of Ramanujan for the Rogers-Ramanujan functions, which I haven't defined, and an unpublished manuscript on highly composite numbers. Okay, if you'll permit me, I'll just conclude with one problem, a famous problem, which is called the Dirichlet divisor problem. So D of n is the number of divisors of the positive integer n. And Dirichlet derived this formula for the sum of D of n less than or equal to x. Here gamma is Euler's constant. So these are the main terms, and this is an error term. You might ask, well, what's this 1/4 doing here? It arises in analytic examinations of the Dirichlet divisor problem, and it just appears there because it appears in analysis. So delta of x is the error term, and finding the order of the error term, a famous unsolved problem, is called the Dirichlet divisor problem. And he showed the error term is big O square root of x as x tends to infinity. So I'm running out of time here, so I won't go through a proof of Dirichlet's result, or how he, but let me go to another identity which connects with that identity in the lost notebook. So J nu is the ordinary Bessel function, and Y nu is a Bessel function defined in terms of J nu in this formula. K nu is another Bessel function which is defined in terms of J. So if n is an integer, we understand these definitions by taking their limits as nu tends to n. Well, these Bessel functions occur in this definition of I nu, which appears in this formula for the error term in Dirichlet's divisor problem. So usually this is the starting point for estimates and improvements of the error term. What one does is to use the asymptotic formula, in particular for y, estimate trigonometric series. So the problem really boils down to estimating a trigonometric series arising from asymptotic formulas of Bessel functions. Well, in Ramanujan's lost notebook, in an unpublished partial manuscripts, he gives another formula. So I give it in Ramanujan's notation, f of x. This would be equivalent to putting a prime on the summation index, where the prime indicates that we take only 1/2 of the terms if x is an integer. So here is Ramanujan's formula. It's a double series involving the same Bessel functions, but it involves an extra parameter theta. So if theta is equal to 0, then this sum just reduces to the sum of d of n over n less than or equal to x. So what Ramanujan has done is to introduce another parameter theta, and we think that he introduced this parameter theta to help him work on the Dirichlet divisor problem. We really don't know if this is true or not. And I've never been able to make any headway on the Dirichlet divisor problem using this identity. So let me make a few remarks. If we invert the order of summation and assume convergence for one value of theta, we can prove the identity for all values. We can also prove the identity for the product of the indices tending to infinity. And this approach is a bit easier than viewing the summation iteratively. So we proved these formulas. Sun Kim, who was a former PhD student of mine, and my colleague Alexander Zaharescu. However, we could not prove the identity as recorded as Ramanujan. So here I indicate that we inverted the order of summation. So this really was the final problem in our analysis of the lost notebook, the final problem, the identity, which was to be proved. So this is my former PhD student, Sun Kim. She's actually one of the top PhD students, one of the best that I've ever had. So the original identity has now actually been proved with myself and Junxian Li, a student of Zaharescu, and our proof was published in 2019. So here is a picture of Junxian Li and my colleague Zaharescu. Well, I said that was the final problem, but let me just say one more thing. So in the lost notebook, there is a formula which was incomplete. So this, remember, theta phi is the classical theta function f of q. So this is a classical result. This is a result of Ramanujan giving the value of phi of e to the minus 7 pi. On page 206 in the publication of the lost notebook, Ramanujan writes, for example, so here instead of 7 pi, we have 7 pi root 7. But he doesn't identify the terms here in his formula. And an identification of these terms has not been made. So there are a couple of results like this which we don't understand, and these still remain unproved. Well, let me skip this last bit and just emphasize that if it were not for Robert Rankin's visit to Mrs. Watson, Ramanujan's lost notebook would have been lost. It's reported that she was going to incinerate all the papers in the attic floor office of her late husband, but Rankin fortunately visited her before she could do that. So let me conclude with a couple passages from a talk that Freeman Dyson made at a meeting on the 100th anniversary of Ramanujan's birth that was held at the University of Illinois in 1987. So he said, I am grateful to the organizers for this conference for bringing me here and giving me a chance to enjoy all the new flowers that have been growing in recent years in Ramanujan's garden. Whenever I am angry or depressed, I pull down the collected papers from the shelf and take a quiet stroll in Ramanujan's garden. I recommend this therapy to all of you who suffer from headaches or jangled nerves. And Ramanujan's papers are not only a good therapy for headaches, they also are full of beautiful ideas which may help you do more interesting mathematics. And maybe they will also help you in this day of COVID-19. So I'm finished with my talk. I'm grateful for the privilege of speaking with you about Ramanujan and his mathematics. I apologize for going over time in my talk.
Okay, well, let's thank Bruce for a very nice talk. Some of us can clap or use the reactions to virtually clap. So let's ask, are there any questions for Bruce?
I just wanted to announce one thing. I just wanted to ask a decorum in this discussion. And I wanted to say that Larry does have the power to mute if anything gets out of hand.
Well, hopefully it won't come to that.
As it has in recent times.
Well, Bruce, I was talking with Hannah after our seminar about the second to last thing you talked about the Dirichlet divisor problem. Mm-hmm. And so that was the last, I think I had heard you say before in a talk that was the last thing from the lost notebooks that didn't have a proof. But right. Hannah had said that maybe there was also, you initially had a proof, right, that was a proof, but was not by your standard in the type of proof that Ramanujan would have discovered. Do you have that proof in the style of Ramanujan or what he might have done?
I'm sure that, well, I think that he might have discovered the proof where the product of the two indices tends to infinity, just because that's easier than the other two proofs.
Okay.
So the other two proofs involve a lot of technicalities in working with the double series. In fact, we had to break up the double series into various intervals and look at the series in different intervals according to the sizes of m and n. Mm-hmm. So the reason it took us so long was that the theorem that we first proved with the order of summation reversed from what Ramanujan had, could not be used at all in the proof of Ramanujan's, the way Ramanujan stated the theorem. Mm. So all three proofs are entirely different, and we can't use anything from one proof in another proof. Mm. We did use techniques of breaking the series up in both proofs, but other than this, but we broke them up in different ways. Mm-hmm. So, except for the proof where the product Mn tends to infinity, yeah, I'm sure that Ramanujan couldn't have devised the other proofs.
Okay. Yeah, I was very curious about I found one of the first things you showed with the identity with swapping the role of sine and cosine, and you said we still don't know what the role of some of the numbers are. Yeah. I haven't seen it. Could you show that again? I think that was like near the very beginning.
Okay, let me just. I must admit, I don't have a scroll here. I'll have to go through very quickly here. Yeah.
Larry, I'm going to make you host now.
Okay.
Okay.
All right.
Thank you very much, Bruce.
Okay.